Hello, I'm Clinton Herget, Senior Solutions Engineer at Snyk. Today's session is called the Developer Desktop Part 2, Building Secure Containers with Snyk. If you haven't already, I encourage you to watch the first session in this series, in which we cover how to use Snyk's developer tools to detect and remediate vulnerabilities in your application's open source dependencies. But in this demo, we'll be focusing on containers. In particular, I'll be showing you how to use Snyk's developer-first tools within your local desktop environment to test your container images for vulnerabilities as you're building them, and how Snyk can remediate those vulnerabilities as part of your developer experience. Over the next two sessions, I'll also be doing a deep dive into how Snyk can provide container security checkpoints within the DevOps pipeline, as well as monitoring your container images for vulnerabilities once they're in production. To start, we'll take a quick look at why it's important to focus on container security within the software development lifecycle, and differentiate Snyk's approach with other container security solutions that aren't built for the developer experience. Next, we'll go over a typical container build process and show how Snyk can seamlessly integrate with your existing local toolchain to provide real-time intelligence into the vulnerabilities inside your container images. We'll look at a sample application and the Docker file used to build its container. Then utilize the Snyk command line interface to scan the resulting image for vulnerabilities, and show two important ways Snyk can help you actually remediate the issues we find. And finally, we'll address the problem of how to ensure you're continuously monitoring your local images for vulnerabilities by linking Snyk CLI to our web application to proactively test your containers and notify you if new security issues are detected in the future. As more and more organizations adopt containerization to deploy their applications and drive digital transformation, it's clear why container security has become so important. But why developer-first container security? Well, first of all, according to our own research, it's because developers are increasingly seen as the group responsible for securing the container image itself. While there are many tools that can contribute to a secure container lifecycle, including ops-focused and real-time threat detection tools, only the developers are close enough to the application code to properly select and customize container images. But beyond that, every vulnerability found and remediated in the development stage is one that's not deployed into production for an ops or a pen testing team to find, which happens much later in the process and without the contextual knowledge of how the application works. And vulnerabilities within container images are a huge problem. We found that over 76% of the top 1,000 most popular containers on Docker Hub have severe known vulnerabilities. And each of the top 10 most popular images has at least 30 vulnerabilities associated with it. In other words, there are far too many potential exploits to fully trust container security to runtime tools. Developers have a critical role to play in ensuring the images that pass through the build process are already as secure as possible, which allows other security solutions to do what they do best. Snyk Container can be implemented across the secure container SDLC, beginning with a local developer's environment through to the Git PR check phase, continuous integration pipeline, and finally continuous monitoring of images for vulnerabilities once they're deployed in production. Today we'll focus on the local developer experience, where remediation cycles are shortest, because you can use Snyk in near real time to get feedback on the dependencies going into your images and the CVEs associated with them. Now, let's get to a demo and see how Snyk can help. So here I'm working on building a web application, which is written in PHP. This is actually the built-in demo app of the Symfony framework for PHP, and it presents a very simple blog type of web app that's in line with contemporary development practices. You can find it on GitHub if you'd like to play along. As a developer in a containerized ecosystem, in addition to building your application, you also define all of the supporting libraries, services, and other utilities that it relies on. If you're using Docker as your container runtime and build tooling, that means creating a Docker file to define those build layers. Snyk Container, by the way, doesn't require that you use Docker, which we'll come back to in a moment, but the two do work very well together. So that's what we'll use in this example. As you may have noticed, this demo app does not ship with its own Docker file. So there are a few ways that I can proceed. At the simplest level, if my application was a statically compiled binary, then it may have no dependencies at all, in which case I could use what's called a scratch or completely empty image that simply contains my binary and nothing else. That's also by far the most secure form of container image, since there can be no vulnerabilities aside from what may already be present in the application. But PHP is an interpreted language, so a scratch image is not an option in our example. For some ecosystems, it may be desirable to use what's called a distroless base image, which are a series of images maintained by Google that focus on the bare minimum viable set of runtime dependencies for a given ecosystem, while eliminating all other packages common to a Linux distribution, such as a shell and a package manager. They can be a great choice if you're using a supported language, but in this case we're not. So we're left with two options. Either we can start with a bare Linux distribution like Ubuntu and individually install every needed dependency, which would be very difficult to maintain in the long term. Or we can go to a resource like Docker Hub and find a base image that's already designed for serving PHP web applications. Then simply make any needed customizations that are specific to our app. And in short, that's the beauty of containers. Because images are layered, it's trivially simple to find an image that has already done most of the work for us. But that's also exactly what makes container images so insecure. Because along with that functionality, we also import all of the vulnerabilities of the base image we choose, and the image it was based on, and so on, with limited to no visibility into their contents. Let's look at an example. I can see in the documentation for the Symfony framework I've chosen that it requires a minimum PHP version of 7.2.9. While that is an older version, as we'll see in just a moment, there are several images on Docker Hub that match, allowing me to choose between various underlying Linux distributions and flavors of runtime. Because I also want to include a web server for my application, I'll use PHP 729-Apache, which also includes the Apache HTTP server. Now, my plans for this blog application include adding the ability for authors to attach images to their posts, which can then be manipulated in various ways. So that feature is going to require some additional dependencies beyond what's available in this base PHP image. So my Docker file for the container looks like this. I'm specifying from PHP 729-Apache as my base image. Then I'm using the run command to install some extra libraries needed for JPEG image manipulation, including GD, libjpeg, and ImageMagick. Those packages are being installed by apt-get since this base image uses Debian Linux as its underlying distribution. And finally, I copy my application code into the container, symlink it to the web root, and then expose port 80 to enable the Apache HTTP server. I build this container in the normal way by running a docker build command and giving the image a tag, in this case Snyk PHP demo. Once that build is completed, it's a simple matter of running the image we just built with a port mapped to my host machine. Once it's running, we start to see logs from the web server process, and then if I load that host port in my browser, I see our application running happily inside its container. And this shows just how easy it is to get up and running with a containerized application. But of course, how secure is it? How do we really know what dependencies exist inside the image we chose, let alone the vulnerabilities associated with them? Here's where Snyk comes in. I'll be using the Snyk command line interface, which is available both as a standalone binary as well as a Node.js package, and is the same CLI used for open source dependency testing, as you may have seen in other demos. I've already authenticated with my Snyk token, which is the only configuration needed. Since I've already built this image locally, testing the image is as simple as running Snyk container test, giving it the name of my image, in this case Snyk PHP demo. Finally, I also want to specify the Docker file I used to build the container. This isn't strictly required, but it does allow Snyk to provide additional context for how to remediate the dependencies or the vulnerabilities that it detects. So we'll go ahead and run this command, at which point Snyk is communicating with my local Docker socket to scan the container file system and construct the dependency tree of all Linux packages it finds within the image. But as I mentioned earlier, Snyk doesn't explicitly require Docker. Any OCI-compliant container image can be scanned for vulnerabilities, simply by specifying the archive file name rather than the image tag as passed to the Snyk container test command. But if you are using Docker, great. In fact, Snyk just announced a partnership with Docker, making Snyk container scanning solution available directly as part of Docker Desktop. Simply make sure you're running the latest version of Docker Desktop, and you should have access to a new subcommand called docker scan, which provides very similar functionality to the Snyk container test command we're using here. Once the dependency tree of your container is resolved, our CLI then queries Snyk's vulnerability database to return a list of all CVEs associated with the packages that are found. You can see how quickly Snyk returns a result. I can scroll up and see a list of every vulnerability inside my container, and there are a whopping 572 of them. So for each vulnerability identified, we include the unique CVE number, the severity according to our security database, a descriptive category of the potential exploit, and the exact version of the package containing the vulnerability, as well as a list of distinct introduction paths, which are routes within your dependency tree through which this package has been required. So there may be more than one for a given package. If you want to know more about a certain vulnerability, we give you a link to our Snyk Intel vulnerability database, which contains our security team's curated intelligence on this particular CVE. But now that I know I have vulnerabilities in my container image, what can I do about them? Here's where Snyk's developer-first approach to container security becomes important, because we've already done the research and given you actionable fix advice wherever there's something you can do to improve the security of your image. Because containers aren't like VMs, it's difficult to simply patch them one vulnerability at a time. If a CVE is found inside your container, it got there one of two ways. Either a package was installed via a user layer, something like a run command inside your Docker file, or that vulnerability already existed within the base image that you chose to build on top of. In the case of a user layer vulnerability, Snyk will identify the line in your Docker file in which the vulnerable package was installed. That's why it's helpful to associate the Docker file on the command line, so we can show exactly where you need to make the associated remediation. In cases where an upgraded version of the package is available, which remediates the vulnerability, we'll indicate it here, so you can refer to that version explicitly when specifying the package to install. But more often than not, vulnerabilities will have existed already in the chosen base image before any user layers were added. In these cases, while it is possible to selectively upgrade individual packages, it's often much easier to upgrade the base image itself, or to utilize a different image tag, meaning a different underlying Linux distribution, or a slimmer variant, one with fewer packages, within that same repository namespace. In these cases, Snyk can offer alternative choices for a more secure base image. If you're using an official Docker image repository, we can show various upgrades that should offer similar compatibility for your application while drastically reducing the vulnerability footprint. As you can see, it looks like I can achieve the same functionality with fewer than half the overall number of CVEs and dropping my high severity vulnerability count substantially. Now, in some cases, especially in large enterprises, developers have to choose from a pre-selected list of hardened images in a private registry, because another team manages those base or middleware images. In these cases, Snyk will soon be able to support customized upgrade recommendations. But in the meantime, it's still possible to identify only the vulnerabilities coming in through user layers by passing the flag exclude base image vulns. This filters the CVE list to only those issues which I, as the developer of the container, can actually control. In this case, because I do have the ability to select a different base image, I'll go ahead and implement Snyk's recommended upgrade. I'll also remove one of the packages that was causing most of my user layer vulnerabilities. It's then a simple matter to rebuild my image and retest with Snyk. While that's running, it's worth pointing out that all of Snyk's output can be customized and easily integrated into other tools. By using the --JSON flag, Snyk will generate machine-readable JSON containing all of the information we've been discussing on CVEs, dependencies, and upgrade recommendations, allowing you to easily reformat the data, write scripts that parse it in various ways, or pipe it into any other process that speaks JSON. There are many open source tools available that utilize Snyk's output to create HTML pages, CSV files, PDFs, and other formats. So Snyk has finished retesting my remediated container image, and I've managed to improve my overall vulnerability count and my high severity issue count substantially from what we saw earlier, which is not bad for changing just 2 lines of code. I can now go ahead and commit this code and create a pull request to merge it in, confident that my container is as secure as possible today. But my work isn't quite done. Because the security landscape is always changing and new vulnerabilities are being discovered and disclosed constantly, I don't want to have to manually rerun Snyk test every day to make sure this image stays up to date. That's why you can also use Snyk CLI to initiate proactive monitoring of a container image. By simply running Snyk container monitor with the same arguments as Snyk test, we'll capture a snapshot of this image's dependency tree and save that artifact in the Snyk web application. This image will then get retested on a daily basis, so that if and when new vulnerabilities are found or new fixes become available to existing CVEs, we'll proactively notify you via email, Slack, or Jira that it's time to update your container without having to manually retest. This way you also get a point-in-time record of a particular build's dependency tree, which you can assign a unique name and refer back to it as you release future versions of your application, all of which will be available in the Snyk UI. I hope you've enjoyed today's talk about securing your local container development workflow with Snyk. In my next 2 sessions, I'll be extending the Snyk container demo to look at the rest of the container SDLC, both integrating within a typical DevOps build and deploy or CI/CD pipeline, as well as how to continuously monitor containers once they're shipped into production. I hope you'll check out those talks as well. Thank you, and as always, stay secure.